Hello, I'm Fabio Rossi, technologist at Italian National Institute of Physics in Genova, Italy. I'm going to show you our work for data reduction in the field of high-energy physics experiment, in particular for the new streaming readout digital acquisition. Let me start giving you some background information. This is the Jefferson Lab in Newport News, Virginia, a particle accelerator known as Continuous Electron Beam Accelerator Facility. It has experiments with large detectors, as usual in the high-energy physics. One of its detectors, for example, is the class 12, placed in the experimental orbit. The detector is a very large equipment, as you can see in the picture, and consists in a lot of different kind of detectors, highlighted with different color in this picture. Each one has hundreds or thousands of acquisition channels with very high data rate. In order to manage this huge data flow, nowadays the acquisition system is based on multiple trigger levels. The first one to remove noise and high-level trigger to reduce the number of acquired signals, keeping only the signal useful for the measure. This mechanism makes decision only on some sector of the entire detector, and it is clear that this approach is prone to lose some data. But in the case of systems like class 12, as we see before, the data loss is manageable and almost negligible. This approach works reliably for almost all physical experiments, but with the new era of high luminosity is more and more prone to lose some data. This is another experiment in its early stage of development, the beam dump experiment, situated in the new hall of the Jefferson Lab. This experiment is going to study the light dark matter. In this case, the detector has less complexity, but it is a large equipment, as you can see, and keeps a quite number of channels, because it has 5 modules of 1000 calorimeter channels and 300 veto channels. Despite the data rate is in the range of 500 megabytes per second and it is manageable from the net, the key difference is the very low rate of useful signal on a very high background noise. In this case, a standard trigger acquisition is not possible, because making decision only on partial information of the detector is prone to lose significant events, and loss some data it is not acceptable due to the scarcity of dark matter events. We expect few events in the entire life of the experiment. A new approach in the streaming readout to solve this problem is this one. We have only the first level trigger to reject noise, and then all the signals are acquired. The trigger, the high level trigger, will be applied only at high level analysis node that knows the entire shot of the detector, an entire time frame of the detector at a specific time. It's a perfect approach to retrieve all the possible information from the detector. But on the other hand, it is a nightmare for the high data rate and for the engineering part. As you can see, each front end in this scheme sends data through a device. In this scheme is a smart switch that must reaggregate the data in order to make possible the parallel execution or the storage. The analysis could be made on a server farm and can manage the high data flux employing more and more servers. The aggregation node and the net, however, have to deal with all the traffic and became very fast the bottleneck for the streaming readout system. Fortunately, none of these network devices use the waveform or the charge information of the acquired signals, but only the timing to build the time frame of the whole detector. With this assumption, it is possible to compress data to reduce dimension. In this slide, we can understand how to use the data reduction node and how it is possible to improve the overall system bandwidth. Immediately after the acquisition, the signal is compressed, a totally transparent operation for the rest of the network nodes, but with less pressure on the device involved. The signal is decompressed only at the end and could be stored compressed as well, saving memory space. But what kind of signals we have to deal, and what is the best data reduction strategy? First of all, this is a typical acquired signal, an impulsive shape with 48 samples. From the physical point of view, it is very important to retrieve information about the timing and the integral of these shapes. In real experiment, the shape of the signal could be more complex. We can see all the possible type of signals, with 1, 2 pulses, very close in some cases, or even overlapped. Fortunately, the probability of these signals decrease very fast with the complexity of signals. We can compress only the first 3 signals and send plain the last one, without affecting the compression ratio. The AI algorithm chosen for the data reduction is the autoencoder. It is an unsupervised machine learning algorithm based on artificial neural network. This algorithm can learn a compression function without any human supervision. It is composed of 2 parts, an encoder to reduce the dimensionality of the input to a latent space that has in each layer few neurons respect to the previous one until the latent space, the compressed layer. The decoder is the exact mirrored copy of the encoder to reconstruct the original data. During the training, the original signals is compared with the reconstructed after the autoencoder in order to find the best weight of each neurons. The training is implemented in Python with TensorFlow and Keras library. This process is lossy, but the loss could be managed and monitored during the process. For example, if the loss of a signal is too large, as for example in this case, the signal could be sent uncompressed and an alert could be set. Later, an expert operator could be manually inspect the particular signal in the optic of symbiotic AI. In order to find the best autoencoder architecture, several tests are carried on, varying the number of neurons in the layer and also the number of layers. The chart on the right shows the behavior varying the number of layers. On the y-axis, we have the loss in percent between the original signal and the reconstructed, and on the x-axis, the layers topology. The chosen architecture is the 2 layers, because the only improvement, little more than 10%, is in the transition between 2 and 3 layers. But it is not considered enough to justify the increase in complexity. We have 10 times the number of weight in the model of 3 layers respect to the 2 layers. The chart on the left instead refers to the variable number of neurons in the hidden layer, and thus the compression ratio. On the y-axis, as in the previous chart, there is the loss in percent, and on the x-axis, the number of neurons. For high compression ratio, in this area, the error in the reconstruction is high and is not acceptable. Error in the order of 1% are achieved for 32 neurons, but in this case is the compression that is not acceptable. Due to the behavior of this curve, a number of 12 neurons is chosen as the best trade-off between compression and loss. This chart, in addition, shows an important behavior of the autoencoder. The compression could be chosen depending on the maximum loss acceptable for the specific experiment. We can move to higher compression, paying little more error. Both charts reports the results for the two types of signal, the single, the double signal, and a mixed dataset as in a real experiment. In order to understand a streaming readout system and the behavior with data reduction, we make a very simple emulator based on Raspberry Pi and laptop as a starting point. It is only an exercise in a manageable and understandable scenario, but this architecture has all the parts of the experimental one and was made such that each node could be easily replaced with a faster hardware. First of all, obviously offline, we developed the autoencoder and trained it with real data. From the AI model, we extract the encoder weights for the compression in C code and the decoder model for the Python decompression. Then, for the real-time test, we build this chain. We analyze now in detail all its parts. The first Raspberry acts as a signal generator, reads the signal from a file at 24,000 signals from real JLab acquisition and with a socket connection send through the network. The second step make the compression. Raspberry receive data, compress it, and send through a second network with another socket. Finally, a Python interface receive the signal, decompress with the decoder model, and build the histogram. At this level with Python code, because we don't have time constraints. This configuration allows only to reach few kilohertz of transmitting data and compression of 4. We are working to improve the compression ratio, but no optimization on rate makes sense with this simple hardware. In this slide, a little bit in detail, the C implementation for the encoder part. The prediction part of the decoder is reduced as a matrix multiplication. The weight from the AI model are used to multiply the input signal, and the biases are added just before applying the activation function. This process is repeated for the number of layers, and the result is the compressed signal ready for the transmission. Now some result of the compression on real signals. In the slide we can see a statistical distribution of the error during the reconstruction of the entire dataset for single blue line and double pulses with the orange line. Error is distributed from less than 1% to a few percent. Signal extracted from the lowest part of the distribution are perfectly overlapped with the original one. But also signal extracted from the upper part of the distribution, despite the few percent of error, are quite overlapped to the original one. The final result shows a mean error in the range from 1.5 to 1.7%, and it is suitable for the majority of the examined experiment. To conclude, some consideration about the comparison with the standard gzip compression. Chart shows the compression ratio among different batch size. Gzip works better for large batch of data because this kind of algorithm checks for repetitive pattern to substitute with symbols, and large batch of data have more probability to have repetitions. The autoencoders instead works quite good for every batch size, especially in our region of interest. In addition, it can work with very little batches. And here some consideration about the execution time. As you can see in the chart, the autoencoder results faster for each batch of data compared with the standard gzip algorithm. Even if the absolute compression time is far from the experimental requirements, the best result in this area are in the order of 20 microseconds per signals. The first attempt to optimize this result is the implementation of the algorithm with multi-thread in order to load execution time, but this happens only for large batches. In the region of interest, highlighted in red, the multi-thread still suffer from the thread split overhead. Other studies are in progress to reach a suitable compression time in the order of 1 microsecond or less. Obviously, both algorithms are implemented with the same code and are tested in the same condition. To decrease the execution time, we actually work on different implementation on powerful hardware, like high-performance Dell server, a parallel implementation on GPU board, and also with the implementation on edge hardware with FPGA and tools like VTC-AI. This closes my presentation. Thank you for your attention.